index where we
Yes,
want
it's
the
going
one?
to say which letter is this.
Okay.
Yeah.
So if it was A to Z, then for A it'd be 1. Or for
Yeah.
B it'd be 2.
Except our list, I don't know exactly what our
Or
list is.
0
There's
or-
100, but yeah.
Okay.
You just have an you just index that list,
Right.
and that would tell you which
Okay, great.
which letter it is, or number, or punctuation. Okay. So this is a GRU cell. So the pink, like if you Google GRU, you won't get this. You'll get GRU, Despicable Me. But I've done that enough. But if you type in GRU cell, you'll get this. The pink is element-wise operations. Yellow is neural network operation, okay? So let's set a hidden state size of 200. What's our X dimension?
It's just
If we have 100 characters in our corpus, or 100 unique characters in our corpus, this would be 100, right? What's our output? 100, okay?
But our output is not H of T, right?
Our output is not, that's a good
The
question.
arrow going to the right.
So our hidden state is going to be our hidden state dimension. Let's say it's 200, that would be 200. But we'd have to run that through another linear layer to get that to 100. Does that make sense?
No.
Yeah, we'll talk about that. We'll get to that later. But remember, what's H, dimension of H?
100.
We set it as 200.
200.
What's X? 100. Okay, if this is going to come out is 100, we have to keep that in mind. Okay, so pink is element-wise, yellow is a neural network layer, okay, a linear combination. So we're going to run our X. We'll start right here. We're going to get this yellow thing that is next, then going to become point-wise multiplied, and then come through here, and then get tan-aged. So if we have a linear layer that's taking in X and H, that's a concatenation. So what does that vector now become? Its dimension?
It's just
300, okay? And then what do we want this, if this is like a neural network layer, what do we want this output to be if it's going to do element-wise with H?
300. No, 200.
200, right? So like we do nn dot linear input 300, output 200. Okay? Then you do like a point-wise multiplication with your H, and then that's still 200, and then you concatenate it again, and then you bring that up there. You also concatenate these again. Oh no.
So you do nn dot linear, nn dot sigmoid.
Well, you do nn dot linear and then a sigmoid, because you have to do a linear combination and then do the activation. Does that make sense? Because think about a neural network layer. You do the linear combination of inputs of X
Oh, yeah.
and then your weights, and then you do the activation. So then you do a sigmoid. Good question. Okay, we concatenate it. When we're concatenating, we're at 300, we decided. We do 300 input. What do we want as output? If it's going to be a hidden point-wise or element-wise operation, it needs to be 200, right? So 300 to 200 linear layer, nn dot sigmoid, 1 minus for 1, and then times that into H, your previous hidden layer. And then go do element-wise times of the output of this guy. So what's going to be the output of this guy? What dimension? Basically, everything out of these yellow is going to be our hidden state dimension, which is 200. Yeah. And the input to all of these will be 300. Or whatever X, the dimension of X plus the dimension of H is, whatever you set that as. Okay, but does that make sense? We're just like, you're concatenating, doing some parameters, multiplication, or neural network stuff, activations, and then element-wise stuff, and then you get your next hidden layer.
So all the hidden layer is doing is concatenating onto your X, your one hot encoded X.
No. Well, that's what these are doing, yes.
Okay.
But, I mean, when you're concatenating here, it's coming from, it's like doing a loop, kind of. So what this is doing, it's like forgetting and remembering. You'll talk about that in class.
Yeah.
But yeah, that's what it's doing.
Okay.
So our output is 200. Now what do we do with that 200? that's our hidden state.
That's your input for the next
Use
iteration.
story.
That's your input for the next iteration, and then if we want an output, what do? We do another linear layer of weighted combination, like a linear layer of 200 to 100. So neural network layer.
Why do we do that? I'm confused with that.
Where's that to get a?
To get our output, because this just gives us our hidden state, right, H? So now we need output, which is a 100-dimensional vector for our
There
character.
should be another yellow box.
So it should be a yellow box. I think we just say use a ReLU. I think you can use sigmoid or ReLU. Does that make sense?
And that should be a normalized vector, right? That because it's just a bunch of probabilities for
Well,
each
no,
character.
H should not.
No. But what I'm saying is the output.
When we output it, you should do a softmax.
Yes.
Which gives us a
You
vector
do that
probability.
right where the arrows diverge at the end? Or?
No, so that's just saying, that's indicating that your hidden layer goes on to the next step as well as going to the output.
Oh.
Yeah.
Say
550.
that again?
So when these, see how this diverges? That's just saying use one copy of H for your output, use the same copy for the next iteration. That's what that's.
Okay, so the copy of H going up, which is your output.
That's not
That's
what's
the
going to
one
be
that's
used
100.
in your output.
What's that?
Because you're going to have another neural network layer
Oh, so that's where the
or another linear combination to go get your
Okay.
output layer.
Let's go
yeah.
from 200 to 100.
Yeah. So I just use
Yeah.
ReLU. You can use
Okay,
Sigmoid.
but before we do that, we're also going to use the one that's 200 in the next layer.
Yeah.
The next iteration.
So you're gonna have to code all that up in your model cell. Does that make sense? So how many sets of parameter vectors do we need? 1, 2, 3, 4, right? There's one hidden up there we can't see, because that's gonna be used to get your output vector. So you have to make 4 parameters, 4 vectors of parameters. Or I guess matrices of parameters, that's my bad.
And that'd be like PyTorch dot.
And well, no, I guess you'd save it as a linear layer. That's what you just save it as. So you just say nn.linear input output, and that saves all your matrices in there.
So how many weights, how many parameters are there on this? Because it sounds like there's a really small number. If there are only 100 and 200.
Well, because if you have an input of 200, output of 300, how many parameters is that? 200 times 300
Yeah, 60,000.
times 4, basically. So that's a good amount of parameters, yeah.
So are there different weights? Looking at the equations, it looks like there's different weights for like the R and different weights for the Z.
Yeah, so this
There's
is a set of weights.
there's like
That's a set of
6.
weights. That's a set of weights. Then it's 1, 2, 3,
3.
and then 4.
Okay, so that's
To
what
get
you're
our
saying
output
is
layer.
the 4 sets of weights.
There's 4 linear layers that you're gonna have to initialize in your model.
And they have like 200 times 300, 200 times 300, 300 times 100.
Yeah,
right? So you
that's
have
okay.
to add all those up.
Yeah, if you want the number of parameters.
Mm-hmm.
These point-wise multiplication or operations, I think you can just use a star and a 1 minus and then use the plus sign. So that should be easy. You'll just create one nn.sigmoid, right? Run both these guys through that object. One nn.tanh. Run this guy through that. So just just implement this picture in your model class, in your forward. So create all the objects of the initializer, right? And then run it through in your forward class.
I think that's for part 3, right? So the first
Part-
couple parts we just use PyTorch as GRU. So it says-
Oh, really?
Yeah, and then part 3, at the end you make your own GRU.
Okay, yeah. So, yes, but you do have to do this for part 3. Yep. So you can just use nn.gru, but
So we can get everything running and then
Yeah.
build
Yeah.
our own GRU.
That makes more sense. Yeah,
Yeah.
design it first.
Yeah.
so here's another hint or helpful tip. So before you start using the Book of Alma, I would just use a corpus of A, B, A, B, A, B, and then just make sure your output can memorize that, or your model can memorize that, right? And start with an A, and it should just be able to memorize that. So that's something that can help. I think that's it. So I would Google this and make sure you understand what's going on here. It's not very clear that these are neural network layers, but that is what's happening, okay? These are linear layers. Peter.
And I think the slides he gave today, they're not up yet, but they should be some point. they have functions of what should be from a written class.
Yeah.
Okay.
He had 4 functions, it was like h tilde equals point one multipliers.
Oh, yeah,
And
yeah.
the Google has, yeah.
So I think that will be helpful in the future for others.
Right.
When it says in our model, when it says decode output, there's like a comment through that line, so we can do that.
Decode. Right here.
Yeah, right there, decode output.
So that means that we need to add that extra linear layer to go from the hidden state to our output layer.
Oh, okay.
Because we're stuck in this hidden state, which we can't understand, and then we decode it into a vector of probabilities corresponding to characters.
So that's just like running it through.
A linear layer.
90 cent linear.
Yeah. And doing don't do a ReLU on that actually. Just run it through and then do the soft
Softness.
Yeah. All right. This is a fun lab. It really is fun. Choosing your own corpus, seeing what it spits out. But you guys got this. Any other last questions?
So just in general, you're gonna train your model on the ALMA text. Do you want to retrain it when you use a different corpus?
Yes.
Okay,
Mhm.
that
Yeah.
makes sense.
Unless you want.
I mean, you can. It can like still learn ALMA, but then it'll mix that in with your next corpus.
Sure.
So
Okay.
what is the init hidden one doing again?
That's initializing your hidden state randomly, or not randomly, but it's just giving you a hidden state of zeros.
So every time it says initialize hidden layers, we can just literally call
Just call that. Yeah.
Oh, just call that one?
Yep. So like
Oh.
he like the guy he like says like he leaves these blank stuffs there, but a lot of it's just like super easy stuff. Yeah. Really, the only tough part of the code is the GRU.
Awesome.
If you know what's going on. Yeah.
So when we were
And you
working,
know Python syntax.
when you're working with the GRU, could you just like somehow do a comparison between nn.gru and yours and make sure it's working out right? Or is it
No, because
just
theirs is written in C. So if you want to go, I guess you can pick up their C code.
It says you can look at the definition. It says don't, but it's probably okay if we like really try and do it. And then,
Their C++ code or C code?
no, well in the lab specs it says